5. So if you, being BC students, I know how you like to get ahead. The worksheet for this is not quite posted yet. Not quite, no. Diana informed me that the link for the worksheet takes you straight back to the notes. So if you start going through the worksheet and you're having deja vu, it's because you're doing the notes again. I will fix that tonight. All right, so this is the first year I've had this section. I used to call it curve sketching. It's kind of the same thing. What we're doing now is we're going to look at putting all the information from the function f, its first derivative, and its second derivative together. Kind of like what we did in one of the ones from the worksheet on the previous section, like the one we worked on this morning, where you had to determine where it was like increasing concave down, and you can make a super chart. And in that super chart, you can put your critical values and your possible inflection values, and you can test the sign of both f prime and f double prime on the intervals in between those, and possibly any discontinuities. And if you have all that information about f prime and f double prime on any given interval, you know what the shape of the graph looks like, right? It's going to look like one of these, right? One of these four pieces. This should actually be a 0. I didn't bring that icon to the front. There it is. And then if you combine that information from the first and second derivative with the function values, the y values, you know then exactly where to place those pieces of the graph. And that's what this big chart up here is just kind of telling you. What happens if f is 0, positive, negative? What happens if f prime is positive, 0, or negative? And what happens if f double prime is positive, 0, or negative? I think you kind of know that. So I'm just going to let you read that on your own, and we'll take 10 minutes right now to do that. Just kidding. Read it on your own, okay? Here, let's jump to example 1. We're bringing everything together from the first derivative, the function, and the second derivative. Okay, sketch a possible graph, meaning that there's not one specific solution, of some function f that satisfies the following conditions. So in this case, we're translating from math to English so we can interpret what to do, and then we're translating it back into math by way of a graph. So here we go. We'll write little notes to ourselves here. If a function f prime is positive on an interval, then we know the function f is doing what on that interval? Increasing. So we're trying to sketch the graph of f, right? So the function's increasing from negative infinity to 1. Is that left or right of 1? Left of 1. F prime is less than 0. That means our function f is decreasing to the right of 1. Okay, cool. So what I would do then is kind of get a sketch, a possible sketch, kind of going, and just add to it as you get more information. Now, without an iPad, we used to use a pencil and just kind of sketched it real faintly so you can kind of see it. It wasn't real easy to do with a dry erase board, any more than it would be with, this. So what I would do, I'll use like yellow on a white background. I wouldn't use white on a white background. What? You could highlight it, but it's not going to be my final graph. Here I know that x equals 1 is a very important value. So just to kind of get a general trend, I know it's going uphill to the left, and it's going downhill to the right. So something like that, yeah? And I don't know where the y values are. I'm looking for trends, right? Now that's definitely not my final graph, because there's 3 ways we can go up and 3 ways we can go down: increasing, decreasing, and constant. So that's what the next piece tells us, something about the concavity, right? If the second derivative is greater than 0, then we know our function is f is concave up, like a cup. And this is going to be to the left of negative 2. So if that's negative 1, this must be negative 2. Okay? And also to the right of positive 2. Okay, that's cool. So I'll need to come over here and have a value for 2. All right, so those are important points where I have them drawn. I might actually come in here and put like a solid dot at 1, because I know that's an important point. Now again, the y values are not that important just yet. I just am marking those x values based upon my yellow lines that I drew there. I also know that the second derivative is less than 0. That means f is concave down like a frown betwixt negative 2 and 2. So down like a frown. Okay, I got that, down like a frown. So I can now connect some of these dots, knowing if it's increasing, decreasing, and concave up or down. it's supposed to be concave up to the left of negative 2. So I got to draw it as an increasing concave up. Now I know it's concave down between negative 2 and 2, and my yellow lines tell me if I'm increasing or decreasing. So I must be then from negative 2 to 1, increasing concave down like frown. And then from 1 to 2, I'm still concave down, but now decreasing. And I know that much right there. And then after that, I know it's concave up again, but I got to be decreasing. So decreasing concave up might look something like that. And it has to go down to, well, it has to go down, decreasing forever. Not necessarily to negative infinity, but it could. All right, so that takes care of that. And then we look at the last piece, and it's telling us, oh, we have some end behaviors that we need to make happen, yeah? As I go out to the left, I need to get closer and closer to negative 2. So I think I could probably salvage my graph here. I'm just going to call this negative 2. That means we're going to have a what there on the graph? A horizontal asymptote. And it would only affect the graph on the left side. Now, if I drew it like that, if I wanted to, since I'm going to a negative infinity, could I decide to be kind of playful and just kind of cross it like that and keep going? Well, if I do that, that's kind of what I want to do. It's my nature. But I would violate these rules, right? Because it has to be strictly increasing everywhere to the left of 1. And when I start jumping around like that, it's increasing, decreasing. So I can't do that. So it has to actually continue being increasing concave up. So in this case, I would approach that horizontal asymptote from above. Got it? All right, and the last piece says when I go out to the right, I need to approach what? 0. That's the what axis? The x-axis. So I'm going to have a horizontal asymptote here. Oops, my graph goes below it. So can I just come up like that? Is that good? Nope, because if I do that now, I've made it increasing, and that's not going to work. So you just have to kind of come back and say, all right, I got it. I'm just going to get rid of this piece here. I'm still going to have it decreasing concave up, but I'm just going to curve it. You might have to adjust some of the other y values too, shift them up or down. What's important is that the x values are where the change happens. Now, I just drew negative 1 there for referencing. It's not really a point on here where anything happens, so it doesn't really need to be there. But there you go. Could you put any discontinuities in there? If I wanted to, could I make this graph holy? Could I put a hole somewhere? I can't because it's differentiable. The second derivative exists on those intervals, and the first derivative exists on those intervals. So guess what that means? It's differentiable everywhere, so it has to be continuous. Yeah, okay. So there you go. That's a possible graph. The only difference really is somebody can make it slightly steeper. Maybe it goes up a little higher than mine, but generally that's kind of the idea. Now, a question like this used to be a nice free response type question on the AP exam, but I haven't seen one where you're constructing a graph in quite a few years. What does that mean? It'll never happen again? No. Could mean that this is the year. Or maybe not. Okay. What's cool is that I'm going to teach you everything you need to know so that whatever they're asking you, you can answer it correctly. Right? And then you can go to college and continue your awesomeness. What? Yeah, sure. Any questions on this one? Example 1, kind of fun? Kind of? You're drawing, right? You should get art credit in here, huh? Art credit. All right, PE credit. We do get a workout. Yeah, The mind burns many, many calories. It sure does. Example 2. If the graph above is the graph of a function on a closed interval, that's a big if. That kind of means let the graph above be that function. Okay, on the closed interval, I see it. On what open intervals is f both decreasing and concave down? So you had a question similar to this in the previous worksheet, but it was from an equation, and we're kind of building up towards that. Decreasing concave down. So if I have the graph above of what? This is where you got to be careful. Is this f or f prime? This is f, right? You always have to understand what is it the graph / equation / table of. So really, I don't have to be looking at things differently. I can just look at the graph and say decreasing concave down. that's going to be something that looks like that, right? That's the only way something can be decreasing concave down. And that's visually what I'm looking for. So is that it? No. Okay. Is this it? No. Okay. How about this? No. Okay. This? Is that the only one? No, there's another one over here, right? Ah. So 2 places. Yay, thank you, thank you. Trial and error. Trial and error. When you have someone there to tell you yes or no. Yeah. All right, so let's go ahead and list -7 union, or -5 union 2 to 3. Good. You could spice that up a little bit by putting x epsilon in front, right? You could. You don't need to though, because we all know that when we say open intervals for a function, we're talking about left to right horizontal x intervals. On what open intervals is the function both increasing concave down? Increasing concave down. Okay, that's going to be like this, yeah? I like to draw it so I know what I'm looking for. Increasing, that's the only way. So I'm looking for that little shape now, that little shape. Hey, how about that? And that one, right? No, no, no. Is that the only one? The green one? I think so, right? -1 to 2 then. -1 to 2. I almost used that as part of the parentheses over here. -1 to 2. Look at that. You can use the increasing concave down. Yeah, this is called recycling, people. I like that. Recycling. Yeah, call me the MacGyver of mathematics. At what x value does f have an inflection point? All right, inflection point. Oh my gosh. Did it say to justify? Please no, please no. No, because that's a lot of writing, right? Where's our first inflection value, the x value? -5, good. Then where? 3? -3? No, -1. And then 2 or 3 or both? 3, good. And then? That's it, very good. There you go, those 3 right there. So there's 3 inflection values. -5, -1, 3. -5, -1, 3. Not so bad, right? It's always a little bit easier when you have the graph. If the graph above is now the graph of f prime, oh boy, that changes things. Oh boy. Now on what open intervals is f increasing? Okay, is this still the graph of f? No, now it's the graph of f prime. So now you want to orient yourself the following way. Y values are the slopes of f. Slopes of f prime are f double prime values of f, concavity values. So f is going to be increasing now when this graph is what? Positive. So -7 to -5, -1 to, do I have to step over 5? It's a little bit different. If it asks you on what intervals is f prime positive, then you would have to step over 5, right? Because obviously if this is the graph of f prime, it's 0 there. But because it says where is it increasing and it's at a single point only 0, we call that a singularity like x cubed, you can actually say it's monotonically increasing through that point. It's a subtle little theoretical difference. So you could go straight through from -1 to 7. And of course the question is, can we step over it if we want to? Could we also say -1 to 5, union 5 to 7? What am I doing? Oh, yeah. I'll come back and get that piece. Yes, I'll come back and get that piece. Thank you. You can actually step over that. Okay? So either one of these. This comes to the definition of monotonic, which if it's a singularity and increasing through the point, you can include it. Now, if it said, again, f prime is strictly greater than 0, which is a slightly different question, then you would have to step over it. Make sense? All right. Yes, and then I would add 2 there. Sorry. I got hung up on that one little part over there. I forgot the left part. I highlighted it. -7 to -5. Union. And then, of course, -7 to -5 union. Now, what if I was doing that and I highlighted it on my graph on the test, but I only listed the right side? Would I still get credit because I highlighted it on the graph? No. Okay. Just checking. I was hoping y'all would be nice and give me at least partial credit, but I understand. Lesson learned. Now, what x values do we have a local min? Local min at x equals -3 and 5. Yeah. Help me out. I have no idea what I'm doing. I'm new here. No, right? That's where f, if that were the graph of f. So local min, we're looking for where f prime changes from negative to positive. So that would be at -1, period, right? Does it say to justify? Yes, f has a local min at x equals -1 since, and we have the argument down now, right? F prime, you can say f prime, you don't have to say the graph of f prime because it is the graph of f prime. F prime changes from negative to positive. Where? At the same place, at x equals -1. So this should be old hat by now. On what open intervals is f concave up? Bless you. Concave up is where this graph is wedding. Increasing. Very good. So from -3 to 2 and 5 to 7. -3 to 2 and 5 to 7. Did it ask to justify? No. But if it did, we'd say because on these intervals, the slopes of f prime are positive, right? We always want to talk about a sign. Hello, Brandon. At what x values does our function f have an inflection point? An inflection point are where the second derivative change signs from either positive to negative or negative to positive. That's where the slopes of this graph do so, yes? So it would be at -3, 2, and any others? 5, right? So remember that the local extrema of f prime, the local max and mins, end up being the inflection values of f, right? The inflection values of f are the local extrema of f prime. So -3, 2, and 5. -3, 2, and 5. Did it ask to justify? Oh yes, darn it. Let's just talk about it because I think y'all have this down. Two of them change for the same reason, yes, at -3 and 5. So you can clump those together. F has inflection values at x equals -3, x equals 5 because the slopes of f prime change from negative to positive at these points. Done. And f also has an inflection value at x equals 2 since the slopes of f prime change from positive to negative at x equals 2. End of sentence. We should get English credit for this class also as well, additionally, too. Yeah, all credit. One class, calculus, right? All day long. Right. Oh my gosh, or OMG, as y'all say, which is fewer syllables. No, it's not. It's the same. OMG. It's less typing, though, right? Less typing. Less thumb workout, right? You have to hit the all caps, though, first, right? Double tap the all caps. That's really 2 there. And then OMG, that's like 5. And then tapping the all caps again to get it off all caps lock. That's 6. Whereas, oh my gosh, would be OH space MY space GOSH 10. So it is more economical. Exclamation point. Yeah. LOL. No. Ha. That's the new LOL, right? If this were actually now the graph of f double prime, that's going to change things, isn't it? We haven't seen one like this, but here it is. Take a good look at it. These y values are now the inflection values of f. Sweet. At what open intervals is our function f both concave? Silly typist. On what open intervals is f of x? I think I was going to ask both concave down and concave up, but I said, no, I'll just ask one. So in what open intervals is our graph concave up? Well, what are we looking for then? Because I'm seeing like a cup right there. We want to know where this graph is what? Positive. Yeah, okay. As long as you know what you're looking for. And the same thing, because it said concave up and it didn't necessarily say second derivative greater than 0, we could do what we did when we were talking about monotonic increasing, right? We can kind of list it from -7 to -5, open interval, and then you can cruise from -5 to 7. You can cruise right through that singularity at 5, okay? I'm not going to write that down. Actually, maybe I will. What am I doing? Oh, that's why everyone's grinning. Calculus all day long. No, we'd be learning a lot of wrong stuff. Concave down like frown. Let me try that again. It's the unhighlighted region. That's what I meant to go for there. The unhighlighted region from -5 to -1. I'm sorry. I'm still amped up from that presentation this morning. Yep. Yeah. Really made me want to jump out there and get some of that, but I didn't bring my board with me. At what x values does f have an inflection point? Inflection point is where the second derivative changes signs. Okay, so that would be -5, positive to negative, and where else? -1. Any others? 5? Is 5 a PIV? Yes. Is it an IV? No, there's no sign change. Okay, good. You got it. And if it asked to justify, please say no, please say no. Ah, it did! They changed for different reasons, so that's 2 sentences. So let's do -5, okay? F has inflection points or values at x equals -5 since, can we just say f double prime here, or do we have to say the graph of the y values of f double prime? Yeah, just the graph is f double prime. Since f double prime changes from positive to negative at x equals -5. Additionally, it has one at the other one since f double prime changes from negative to positive there. So I wish you were able to just clump them together because, again, we don't make a distinction between inflection points, or at least I don't know of a name for one where it curves up to down and versus down to up. But we still talk about how it changes. That's kind of the spirit. That's the idea. What time do we get out of here? Anyone know? I'm all turned around. 5 minutes? Okay. I don't think we have time. So let's just stop right there. We got through example 2. This is all good training for the test that we'll actually have when we get back from Thanksgiving break on that Tuesday. So.